Today we will be talking about Lab 5, Choose Your Own Adventure. For my adventure, I chose to model collisions. The objective of my lab was to observe the behavior between two equal masses before and after a collision. I wanted to determine if the collision was elastic or inelastic, and then comment on conservation of momentum throughout the collision. I found that the momentum is in fact conserved, the collision is elastic, and thermal energy will not significantly increase from the collision. Some assumptions that I had to make before moving forward. I assumed that the balls were going to collide in one dimension, the x dimension. I set the system to be the two balls and the surroundings would be everything else. Lastly, I made the assumption that the energy transfer between the surroundings and the system is negligible compared to the interaction between the masses during the collision. This is a smart assumption to make because we can set delta E equal to 0. Some relevant concepts that we need to understand the problem. Conservation of momentum. Conservation of momentum states that the total momentum before the collision must equal the total momentum after the collision. If there are no external interactions, then F net will equal 0. And thus, according to the momentum principle, dp dt will also equal 0, and thus momentum is conserved. Next, the conservation of energy. As we stated earlier, we can set delta E equal to 0 because there are negligible interactions between the system and the surroundings. If the change in kinetic energy is also 0, then we have an elastic collision. However, if the change in kinetic energy is non-zero, there is an inelastic collision. This would mean that thermal energy would increase and the temperature would rise due to the collision. Now we will look at our original video in Tracker. I have set the right side of the axis to be the positive x direction and the left side to be the negative x direction. The ball to the left is mass A and the ball to the right is mass B. If we set the observed motion of each ball together, we see that mass B, the red line, starts with a negative velocity and then after the collision turns into a positive velocity. This makes sense because it is headed in the negative direction at first and then after the collision turns into the positive direction. The reverse is true for mass B. We should note that Tracker does not capture the instantaneous moment of the collision. This could lead to errors when calculating the conservation of momentum. Since we cannot evaluate the total momentum at the moment of interaction, we will assume that we will take the data right before and right after the collision. If we run the calculations for the conservation of momentum, we see that the sum of momentum right before the collision equals the sum of momentum right after the collision. This means that momentum is conserved. Next, we want to see if it is elastic or inelastic. By determining K final and K initial for both balls and summing the two together, we see that delta K of the entire system is 0, and therefore the collision is elastic. Since delta E is 0 and delta K is 0, this means that delta E thermal must also equal 0, and thus there is not a significant increase in temperature due to this collision. To run the expected motion, I wrote two codes in VPython, one modeling pre-collision and one modeling post-collision. All I did was I wanted to find what the expected position of the balls would be prior to the collision and then after the collision. I did this using, as we see here, Newton's fundamental principle. Similarly, to find the motion after the collision, I used Newton's fundamental principle to model the position after the collision. We see that the graphs look very similar, the expected motion looks very similar to the observed motion. However, it is still not a very good estimate because the change in velocity, although it is constant, is changing at a different rate than what we observe. However, I still found that momentum is conserved during the expected collision and the collision is still elastic. What if? What if I had not assumed that there was negligible energy transfer between surroundings and the system? Well, then the change in total energy would not be 0, and there would be a non-zero change in thermal energy. Similarly, what if I hadn't assumed that the collision was in one dimension? After running calculations for this case, the true case, momentum is still conserved. However, the collision is not elastic. and thus there is an increase in thermal energy and an increase in temperature. We see here, after seeing the x direction and the y direction, that the movement in the y plane is not constant, and thus this means that the movement in the z plane is not constant since the table is flat. In conclusion, the momentum of the system is conserved because the total momentum before the collision is equal to the total momentum after. Also, the actual moment of collision, it was not captured, and thus we cannot completely comment on an accurate picture of the collision. Next, the crash is elastic because the kinetic energy does not change from before to after the crash. And lastly, there is not a significant temperature rise caused by the crash. Thank you.